Yeah, visible now.
Okay. So we'll start with Chordal graphs.
Oh, Chordal. Chordal.
Right. Okay. Let us see the definition. Okay. So it's saying graph G is simplicial. So this is also a new notation. Simplicial.
Simply so.
Right. So a vertex is called simplicial if its neighborhood in G induces a click. So click, if you remember, it is a complete graph, right? So
Correct.
so suppose this is a particular vertex U.
Can you remember remind again? Correct.
Yes. So this is a complete graph.
Complete. Complete.
So complete graph, if it occurs as a subgraph in a bigger graph, we call it as a click.
Uh,
Okay.
that's when we reduce vertices S. The color we reduce is right.
Yes, yes. Click is so in that particular subgraph. If we restrict to that subgraph, every vertex is connected to every vertex. That is
Okay.
a that is same as that click, right?
Correct. KN is right.
Yes, yes. Kn
Oh,
is a complete graph, but if it occurs as a subgraph, then it is a click. Yes.
ah, mm-mm. Yeah.
Okay. So yes. So for example, suppose you have you. This is you, and suppose this is your neighbor of you, right? So u is only adjacent to inside vertices, right? And suppose this is your bigger graph. So this is
Ah,
your original graph. But suppose if I consider this part only, so suppose this is a complete graph. Suppose kn, that is it is a click.
ah,
That is here we have the size of the neighbor is n. The number of vertices in the neighbor of u is n, and it forms a click. Then we tell that this vertex u is simplicial. Okay.
simply so if its neighborhood
Yes.
in the include clip, that means
Yes.
clip plus something is right.
Yes. Yes. The bigger graph is something else, but if we restrict on the neighborhood, it is a click.
Mm, mm.
Okay.
That means, for example, we you have two S, two neighborhood. One
Okay.
neighborhood is a three neighborhood, and two neighborhood is click, and
Okay.
other one is not click. That's the on that's the also okay, right?
No, the thing is, so neighborhood means, this neighbor of u. I am considering all the vertices that is adjacent to u in this graph. I am taking all those vertices
In
in the
combining
in the whole graph. The
in a
G.
click, not
No,
two
in the
click.
G, in the whole graph, I am looking at the neighbor.
Uh,
Neighbor n of u is the neighbor of u, right?
mm,
So I am looking to the whole graph,
okay. Okay. I got it. Got it.
right? So if I
Okay.
so n of u is nothing but a set of vertices, right?
Mm,
So if I restrict to that set of vertices, then that is a click. Then I say that U is a simplicial vertex.
okay. Got it.
Right. So next definition is a simplicial elimination order. So this is one more definition. So it is called Simplicial elimination order. So is an ordering. Suppose ordering of vertices. So let us write. So Vn minus 1 like that up to V1 for deletion of vertices, so that each vertex Vi suppose is a simplicial vertex of the remaining graph. Okay, induced by V1, V2 up to Vi. So yes, so the thing is ordering is starting from the in a decreasing order. So you are starting from Vn minus 1 up to V1, such that if I gradually delete one vertex, so first at first stage I will delete Vn, in the next step I will delete Vn minus 1 like this. So at every step, suppose I am stopping at the ith step, so then I have only the set of vertices V1 up to this Vi. If I take this, then Vi must be a simplicial vertex of the remaining graph. So it means, if I try to explain more, so it may happen. So when I have the full graph, then it may happen some of the vertex, suppose V3 or V4, is not a simplicial vertex. It can happen.
Mm. Mm.
But when I delete the bigger vertices according to the ordering, then from the remaining graph, what is left, it can be your simplicial vertex. It is a simplicial vertex.
Wait. Vn, Vi, V1 for relation of versus so that each vertex Vi meaning right in the silver V1 V2 Vi. Can we have example?
Yes, yes. Example we'll see. We'll see some observations and then see an example. Okay.
Mm. Mm.
So up to this is fine then. Okay. So the thing is, in a tree, if you take any tree, a simplicial elimination ordering. So it is given by. So is a successive deletion of the leaves. Right. So here we can see it. What is happening? This is an example. So, uh, so let us see an example. Suppose we take any tree. Let us take a small example. So here I have to give an ordering to the vertices, right?
Uh,
Okay. So, so suppose if I so there are how many vertices? So here is 1, 2, 3, 4, 5,
two, three,
7.
4, 5, 6,
Right.
7.
So I have to name the vertices in the ordering up to from V1 to V7, right?
Mm.
Okay. So if I name this vertex V7, right? So then V7. So what is the neighbor of V7? So V7 is only this one, right?
Mm.
So the neighbor of V7 is only the single vertex, this one, right?
Yeah.
So individually, if there is only one vertex, it is a clique, right? Because it is just K1,
Mm.
right?
Mm.
So we can first name all the pendant vertices, or these leaves. These are the leaves, right? So V7, this I can name V6, V5, and V4. right?
mm,
So we can start deleting this one, then this one, then this one, and this one. That is not a problem. Now after deleting this four, this and this becomes a pendant vertex, right? So I can name this one as v3, this is v2, and finally I can name this v1. So if I give this particular type of ordering, then you can see that it satisfies the definition. So this is actually a simplicial elimination ordering.
remember is Simplicial. But does G have seven vertices?
Yes.
We
So
delete V7. We have V3.
yes, v3 is the only neighbor. So if I so that is correct, right? V7, the neighbor of v7 is v3, and it is a clique, right? So
V,
v7 is a
v
simplicial vertex.
V7 V7 is simply CO is right.
Yes, v7 is a simplicial vertex, right? So now
Ah,
we delete that. So
that's
we
big.
delete v7. Now we look into the remaining tree. Remaining tree, what is the highest vertex? V6,
Mm,
according to the decreasing ordering, right?
mm,
So v6 is also same idea. V6 is also a simplicial vertex for the remaining tree,
yeah, yeah.
right? So like this, I can delete all these pendant vertices. Now, if I look into this tree as a whole, right? Now, what is the neighbor of v3?
Neighbor V3 is V1, V7 basis.
Right. So v1, v7, and v6. So here you can see that it is not a simplicial vertex, right? Because v1, v6, and v7, this does not form a clique, right?
Mm, mm,
So it is not a simplicial vertex in the whole graph, right?
mm,
But as we continue the deleting process, after deleting all the pendant vertices, I have only left with this much, right?
mm,
I am only left with v1, v2, and v3, right?
mm,
After deleting all these pendant vertices, right?
mm,
So then you can see that v3 is a simplicial vertex in this remaining graph. So that
mm,
is what they are stating in the thing, right? So vi is a simplicial vertex in the remaining graph.
mm, mm, mm.
Okay.
But V2 as well, but V1 is not simply zero.
Yes, yes. Till now, v1 is not simplicial. So, but v2 is also simplicial. So I can delete v3. Then I delete v2. Now only one vertex is left. That is automatically satisfies the property because
Ah,
the neighbor is the empty set.
ah, yeah,
Fine.
yeah, yeah, yeah.
Right. So now, yes. So the one point that you can recall here is so this is fine. So if you recall the chromatic polynomial mm, of g and k, where g is a n vertex tree. So this is k times into k minus 1 to the power n minus 1, right? Where g is a tree on n vertices, right?
Mm,
So we'll see what is happening here. Okay. So actually now we'll use this simplicial ordering to count the thing. So let us see. So when suppose v1, v2 up to vn is a simplicial elimination ordering. Uh, for g, so we can apply the product rule because to count the proper number of k calories. So the product rule of elementary combinatorics So just we can apply the product rule to count the total number of.
Mm.
So allows us total number of proper k colorings.
Mm.
Right. So the thing is, so suppose, so how to use this? So if we have, so if we have colored v1, v2 up to, suppose we have colored up to vi, right? Then so when we add this vi, this vertex, right? There are k minus degree of I number of colors. There are number of ways to color the vertex I, right?
Mm.
Right. So
Mm.
there are k minus degree I number of ways to color this vertex I, right?
Mm. Yeah.
So so the what is di? Di is nothing but so this di is nothing but the neighborhood of vi minus, or you can say intersection with v1, v2 up to vi minus 1.
Oh.
Okay.
Mm.
So the thing is, we are while choosing the colors, we are starting from the first vertex. So so this one, let us do one example, then it will be clear. So here, after this stage, we have only left with this v1 and v2, and
Mm.
then finally after this, I am left with only v1. Right.
Mm.
So now this v1 has k choices, right? Because it is nothing, it is adjacent to nothing, right?
Uh,
Because suppose we are given k colors, then v1 has k choices. Now v1 has k choices. This must have k minus 1 choices because I cannot take the same color of v1, right?
right.
Right. So now if I go back, it has k choices. It has k minus 1 choices. Now
Uh,
it has again k minus 1 choices, right?
okay.
So like that, we will go back now to the original tree. So
Mm.
that is what we are saying.
Mm. K minus di.
Right.
K minus di.
Right.
Right.
So here di is one only, right? Because if
Mm.
we check for the particular case of a tree, so then di is nothing but vi intersection what is there up to previous, or v1 v2 up to vi minus 1, right? So
Mm.
here you can check the d of 2 is 1, d of 3 is also 1, because it is attached to only
Mm.
one of the previous ones, right?
Mm.
Right. So what is happening is, so di we got, so this factor k minus di, so this is independent. It is independent of how we choose the previous colors. Previous colors are chosen because since we are backtracking, right? So since we are backtracking, I know that at every stage, this vi, it is a simplicial vertex to the remaining graph, right?
Mm.
Right. So since vi is a simplicial vertex to the remaining graph, I cannot choose this many colors, right? So I have only choices of k minus di colors,
Mm.
right?
Mm. Mm.
So that's how it gives. We'll see. So for tree, it becomes easier because at every stage it is adjacent to only one. So that's why I have this thing k into k minus 1 to the power n minus 1. So
Mm.
we'll see a different graph and example. It will be more clear.
Mm.
Okay. So let me complete this. previous colors of chosen. Because the neighbor of vi
Mm.
that have been colored form a clique of size di,
Mm.
right, and have distinct colors. Fine.
Mm. Mm. It's okay. Mm.
Right. So let us see an example that is not a tree. What is happening?
Mm.
So let us take this graph. Okay. Can you give a simplicial elimination ordering to this graph? So we have to first order the vertices, right? So can you give an ordering? So how many vertices are there? So first of all, there are six vertices, right? So I have to give an ordering v1, v2, v3 up to v6. I have to give an ordering. So at every stage, such that if I delete, it should be the neighbor should be a click.
Mm. V1.
Yes, v1 we have to start with
Tap
the larger vertex.
the list, right? The last.
Leaf what you want to give?
Any other, we have to consider about the other.
Yes, yes, because we are starting from the bigger thing, right? So
Uh,
v6. So for example, if you remember, so here I gave. We started with v7, right?
which one? Yeah.
Yes, yes.
So here the first is the which
Which one?
in the left bottom
Left to bottom. Okay.
is
So if I
right.
give, let us try it. So this is v6 then.
We delete
So
it.
yes, still now it is correct because if I delete v6, its neighbor is only single vertex. So it is a click. Then that is v5.
We find we find click click delete we find. Ah, the neighbor of this
Okay. So if I give it
uh,
v5,
we delete
so I
it.
have already deleted it. So
That's
the neighbor of v5 is these three vertex, right?
yeah. That's the
And
K3.
yes, yes. So that is working. So yes, that is v5. Then
Yeah, yeah.
v4.
We find we found above of we find
Okay. So this you are saying v4. Let us check. So now this
K2.
is not there. So this is not there. This is not there. So my graph is this much.
We have a K2.
Yes, before neighbor is k2. Yes, that is fine.
K2, K2. And the right of K4 are the any neighbor of V4
Yes,
is okay. We have also K2. Yeah,
right.
V1. Yeah.
So this is v2 and this is v1. This you can do, right?
Mm,
Fine.
yeah, it's okay.
Okay. So now let us check what is the chromatic
Coloring.
polynomial. So how to bring the chromatic polynomial, right? Okay. So we can start with the v6. So v6 has k choices, so that is
K,
not a problem, right?
K.
So this has k choices.
And V5 is K minus degree, is right.
Right. So k minus
K minus
1, right?
degree 1, 2, 3, 4. minus one. Uh,
right? So here, okay, this is k minus one, right?
mm,
Because we are adding back, right? Okay, then
k minus one as well.
so now
V4,
v4 is also k minus one
k
because
minus one. Yeah.
right, but
V2
v3
or
becomes k minus 2.
V3, k minus two.
Okay,
K minus two. K minus three.
this becomes k minus 3 because the number of adjacent vertices is 1, 2, 3. It has to be different from that, so it is k minus 3, right?
First V1 is k minus two.
Right. So this is k minus 2. So from here we can reconstruct the graph, and hence the chromatic polynomial is. So this is k into k minus 1 square, k minus 2 square, k minus 3. Right.
Mm,
So this gives me the chromatic polynomial. Right.
yeah.
So the simplicial elimination ordering helps us to find the chromatic polynomial of a graph. Right.
But k minus di.
Right.
When we use k minus di, way
So
to
here
write
actually
it.
we use right k minus di because let us check. So v6, right? What is the so v6? What is the d6 then? D6 is 0,
One,
right? No,
zero.
no, 0
Uh,
because it is the starting thing, right?
uh, uh.
So I have
But we find
d6 is 0, right?
uh,
So d5 is what? So d5 by definition, so
four.
d5 is neighbor of v5 intersection with how many vertices we
Okay,
have
okay, okay.
covered.
I misunderstood. I think di is the degree of I, but not. Yeah. Okay.
Okay, so in fact, actually, this is okay. This is not exactly correct. So we actually are starting from v1.
Mm,
So yes, we can reverse the process, but that will be most more or less it is the same.
mm, 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 mm,
Okay.
mm, mm. Neighborhood of vi.
Yes, yes. So more
Intersect
it will
with
be
v.
yes.
Okay.
So it will be more correct if I do like this. So let me copy the graph. Okay, if I this chromatic polynomial is correct, so that is not a problem. But if I name these vertices like this, then it will be easier for me. So if I this is v1, this is v2, this is v3, v4, v5, and v6, then it is easier for me to construct. So then I can start with v1. It has k choices,
Ah,
right? Then d1 becomes 0. So d1 is 0. So now if I look at d2, so that is 1, right? So it becomes k minus 1.
one.
Now
V2 E1. V2 E1.
right, right. So
Oh,
d3,
what?
the adjacency with d3 v3 is only v2, right? So it
V3
is also 1.
V2 1. Ah,
So this is k minus 1. Now d4. So d4 is adjacent to v2 and v3. So it is 2, right?
okay.
So it becomes k minus 2. Now d5, v5 is adjacent to v4, v2, and v3. So it is 3, and it becomes k minus 3. And d6 is 2 again because it is adjacent to only v3 and v5. So it becomes k minus 2. So same idea, more or less the same idea. The polynomial is also same. Okay.
Mm, mm, mm. Yeah, it's okay.
Fine.
Mm.
Okay. Then so then what is happening is so up to this is fine. Okay. Then let us see one remark. So some graphs we can actually have. So actually, what is happening is, so if we have a such simplicial elimination ordering, I can express the chromatic polynomial as a product of linear factors, right? Like this.
Mm.
So these are actually product of linear factors, right? So
Product of linear factor.
yes, so each of them is a product, right? So actually means the chromatic polynomial is any function of k, right? Where k is the number of colors,
Mm.
right? So what you can do is, so it need not be happen that it can be written in this product form. It can be something, some function of k plus some function like this, right?
Mm.
It can happen like that also, right?
Yeah.
Okay, so that is the remark. That is the next remark. That is based on that observation. So it is important to note that some graphs without simplicial elimination ordering also. So for it is possible that every graph may not have this ordering, simplicial elimination ordering.
Mm.
Also have chromatic polynomial.
Mm.
That can be expressed as product of linear factors. This type of that of the k minus ri form like this, where these ri's are non-negative integers. So this is just an observation. That is fine. So I think this example is clear. Right?
Mm.
Okay. So you remember this interval graph, right?
Mm.
Interval graph we defined, right? So that is also an example of graphs that has simplicial elimination ordering. Okay. But the thing is, an example of a graph where simplicial elimination ordering does not work is a cycle. So that we also need an example, right, where it does not work.
Mm.
So when n is greater than equals to 3, the cycle graph Cn has no simplicial elimination ordering.
Mm.
Okay,
Mm. It's okay. Mm.
fine.
Mm. Yeah, yeah, yeah. Mm. N greater than 3, greater
Right,
than 3.
right.
Cn. Ah, Cn. Mm.
Yes.
So we can
Actually, you can more.
in
You
the
can. I think it is strictly greater than. So here, the thing is, so if you take a C4,
C4 from C4.
yes, yes, yes. So if you take a C4, then actually you cannot choose the first vertex itself, right? Because if I want to choose this one, then these are the neighbors, and this is not click, right?
Ah.
I cannot choose any vertex, right? So that is the idea. So ordering, since a cycle has no simplicial vertex to start with, we cannot start itself to start the elimination, right? So these two vertex, if I this is not a click, so it does not have, right?
Mm.
So this is also one condition that so if I want to have a graph where simplicial elimination ordering exists, it should not have any cycle as a subgraph. So that is also one condition.
Yeah, since cycle had not since
Right.
choose that
So the
way.
existence of simplicial, I write it down simple form, simplicial elimination ordering
Mm.
is equivalent to the absence of such cycles as a induced subgraph. Right.
Mm.
I think up to this is fine, right?
Ah.
Okay. So next we define. So next we have another definition. So we define what is a chord of a graph. So or chord of a cycle we will define. So a chord. So this is the definition of a cycle C is an edge not in C. So it is not a part of the cycle whose endpoints lie in C. So it is not a part of the cycle, but it uses the endpoints of a cycle. So for example, so if we take this 4 cycle only, C4. So then, so this is the cycle. These are the vertices. Then suppose I have this edge, right? So this is
Mm.
not a part of the cycle. So this I will say chord. Okay,
Mm.
fine.
Mm. Yeah.
Right. So usually then a natural
Core.
thing,
Mm. Core. Mm.
yes,
Yeah. Yeah. Yeah.
right. So
Yeah.
natural question asks the natural definition that follows is what is a chordless cycle? So
Core. Ego. Core.
a chordless cycle. Yeah, so from the name it follows itself. So is a so in G is a cycle of length at least 4 in G that has no chord. And so now we'll define what when a graph is called chordal. So a graph G is chordal. A graph is chordal if it is simple and has no chordless cycle. So if it have a cycle as a induced subgraph, it must have a chord. So then we'll say
Ah, Chordal Graph. Mm.
right. So then we'll say it is a chordal graph.
Wait, colon cycle in the here cycle of length of at least 4
Right.
in the that no call symbol and has no colon cycle. Colon cycle. A cycle
Right.
at least length 4 and no call. Ah, yeah, yeah,
Fine.
yeah, yeah, yeah. For example, sway is colon cycle is right.
Yes.
Ah,
C4.
C4.
No, C4 is a chordless cycle, right? Because it does not have a chord. So if I
Yeah, yeah, yeah.
give this chord,
C4 is colon cycle.
yes, it is chordless because C4 if I take
Colon
individually, it is chordless because it does not have. So if I take this one, then it is a chordal graph because this is a chord.
Mm. Uh,
Right. So
Cardinal.
actually, the motivation for defining a chord, if you remember, it comes from geometry, right? So geometry, when I have a cycle or a normal circle, if I draw some line like this, it is a chord, right? So
Mm.
diameter, the diametric line is a special type of chord, right?
Ah, ah, ah.
So that comes, the idea comes from there.
Mm. Mm, mm. Caudal, caudal, sway is called cycle, and sway is also caudal.
Yes.
Mm. A symbol. Mm. Symbol. Yeah. No luck.
Okay.
Mm. Yeah, it's okay.
Okay. So next there is a lemma. So the lemma says that so for every vertex x in a chordal graph G, there is a simplicial vertex of G among the vertices
Mm.
farthest from X in G. Okay. So is the statement fine?
For every status, wait. See, yeah, from X to Z in Z.
Fine.
However, you wrote it X in Chordal. Hmm. There is a Simplicial.
Yes. So there is a simplicial vertex. So that will be if, farthest among the vertices in the farthest from G, farthest from X in the graph G.
Mm, mm, mm. Yeah, yeah, yeah.
Okay.
Okay, okay. Lemma.
Right. So let us see the proof.
We conclude that there is a Simplicial conflict of Z
Yes.
among the vertices. Yeah.
Farthest from X. So it is in the farthest in the distance notion. So
Uh,
it should be in the farthest vertices from that uh, point particular vertex X.
mm, yeah.
Okay. So the proof will use induction on the number of vertices.
Uh, from C4 or
No,
no?
no, any graph, any graph,
Any?
any graph. Yes. So we use induction on n of g. That is the number of vertices. So base step is so this is ng equals to one. So if there is one vertex, then the graph is nothing but a single isolated vertex, right? K1, and it is simplicial. So
K1
there
is
is
caudal.
only one single vertex.
That's also the caudal.
Yes, yes. That is also chordal. Also, the thing is you don't have any other thing.
Mm, mm,
Okay.
mm,
Any other age or adjacency is not there. Right.
mm,
So that is true. for the base step is true, automatically true. Now the induction step. So here we assume that the number of vertices is at least 2, right?
Mm.
So we have to show it is true for every vertex, right? So we have to do some case work. So if x is adjacent to all other vertices, then we just apply induction hypothesis. So we apply the induction hypothesis to the chordal graph. G minus x, right? So if we delete this x and consider g minus x, it is still chordal, right? So it does not violate any property. So we'll apply induction hypothesis on g minus x, and each vertex, so each simplicial vertex y of g minus x is also simplicial, right?
Eliminate is also simple.
In G, right? Because that is not affecting the structure because X is adjacent to every vertex. So
Mm.
since X is adjacent to all of neighbor of Y, union that Y also, right? So any vertex that is simplicial in G minus X is also simplicial in G. So I can take that vertex and that will satisfy my condition that I will find a vertex that is among the farthest of G because X is adjacent to every vertex of other vertex, so that is not a problem, right?
Mm. Mm.
Okay. So now the other condition remain that what happens if X is not adjacent to every vertex, right?
Mm.
Okay. So that will take some time. So maybe we will do in the next.
Ah, okay.
Okay. So we'll stop here.